My name is Dr. Vladislav Steyman. I would like to present you our research Analytical Approximation for Photonic Array Modes in one-dimensional photonic devices. The object of the research is electro-optical components of one-dimensional cross-section, including a large number of coupled optical waveguides or phased lasers. They belong to a specific class of so-called one-dimensional photonic crystals. The light is confined along x-axis of the device and propagates along its optical axis, namely z-axis. Here you see examples of one-dimensional array of coupled waveguides and one-dimensional array of phased lasers. The research was conducted by me, Dr. Vladislav Steyman. I'm with the Electrical Engineering Department of Braude College, Carmiel, Israel. Professor Eli Capone, he's with the Physics Department of Swiss Federal Institute of Technology, Lausanne, Swiss. Professor Amos Hardy, he's with the Electrical Engineering Physical Electronics Department of Tel Aviv University, Tel Aviv, Israel. And our students, Elena Smith, she's with the Electrical Engineering Physical Electronics Department of Tel Aviv University and Electrical Engineering Department of Braude College. And Lidor Giladi, he's with the Electrical Engineering Department of Braude College. The purpose of the research was to develop a full analytical description of array modes, which should include electromagnetic fields and propagation constants, for large one-dimensional photonic crystals, namely devices containing a large number of coupled waveguides or lasers in which light is confined along x direction and propagates along the optical axis or z direction of the device. The description should cover both photonic lattices. Here the example of photonic lattice, which is periodic array of identical waveguides or lasers, and photonic superlattices. Here you see an example of photonic superlattice, periodic sequence of different waveguides or lasers. A unit cell of photonic lattice is a solitary waveguide or solitary laser. A unit cell of a superlattice is a supercell, a minimal periodic sequence of different waveguides or lasers. Theoretical background: coupled mode theory. Let me start from a very basic assumption, which is called modes expansion conjecture. This conjecture states that transverse component of the array mode, confined along x-axis and propagating along z-axis, is nothing but linear combination of transverse components of all guided modes of all solitary waveguides in all unit cells of the array, multiplied each by partial amplitude and by running wave exponent in power I sigma z, where sigma is a propagation constant of the array mode. In this expansion, guided modes of solitary waveguides are supposed to be known in advance. Thus, in order to reconstruct a transverse component of the array mode, we only need to know propagation constant of the array mode, sigma, and a set of partial amplitudes, or so-called envelope function of the array mode. Note that this expansion holds both for lattices and superlattices. For superlattices, it holds as is. For lattices, in other words, for arrays of identical waveguides, it also holds if we put a total number of waveguides in a unit cell S to be identically equal to unity. For superlattice, S must be at least 2. Let me show you how modes expansion conjecture works. Consider array of 12 identical single mode waveguides. Number of unit cells in this array is 12. Number of individual waveguides in a unit cell is 1. Number of guided modes in this single waveguide is 1 as well. This array should support 12 array modes. Thus, there will be 12 different envelope functions U0. Each contains 12 components. We assume that guided modes of individual waveguides are known in advance. This is model field of a guided mode of a solitary waveguide. Its propagation constant is known in advance as well. We are to find envelopes U0 and propagation constants of the array modes sigma. Here you see envelope function for array mode number 1 and envelope function for array mode number 2. If envelope functions and propagation constants are computed, we can reconstruct the full array modes fields with the modes expansion conjecture. Here you see a model field of array mode number 1 and model field of array mode number 2. Computation of array modes. As I already said, in order to reconstruct the full set of array modes supported by the device, it is necessary to compute the full set of envelopes and their associated propagation constants. There are two options to do that. The first one is a standard coupled mode theory approach. This approach requires solution of a coupled mode eigenequation for U0 envelope functions and sigma propagation constants. M matrix M times U0 equals to sigma times U0, where M is coupling matrix whose elements describe pairwise interaction between all guided modes of all individual waveguides. There is another option, analytical approximation, for array modes containing a large number of unit cells, solitary waveguides for lattices or supercells for superlattices. Find U0 and sigma analytically without computation of coupling matrix M and subsequent solution of coupled mode eigenequation. Analytical approximation. Main idea of the analytical approximation. There are some basic assumptions we use in our approximation. First, the leak of the model fields outside the photonic array is negligible. Second, one-dimensional photonic array of identical unit cells, namely identical waveguides, for lattices or supercells for superlattices, can be roughly approximated by a single auxiliary envelope planar waveguide, curve number 2. The width and the core-clad contrast of the auxiliary waveguide are equal to those of the original array. Third, for an array containing a large number of unit cells, n, the envelopes u0 and the propagation constants, sigma, can be approximated on the basis of the guided modes of this auxiliary planar waveguide, discretized at the centers of the unit cells. In order to understand in a simple way the main idea of our analytical approximation, let me remind you eigenmodes of a high contrast planar waveguide of width of L, or a chain of length of L containing n identical links of width of lambda. In both the cases, the first n eigenmodes of the systems have a form psi-q as a function of x equals to aq times sinus pi qx over lambda, or aq times sinus kxq x. Here kxq is a qth wave number or qth spatial frequency. Kxq equals to pi q over L, and q is a discrete number running from 1 to n. aq is an amplitude of the qth harmonic. In case of a chain containing a finite number of coupled elements, links, n elements, each element of width of lambda, kxq equals to pi q over n lambda. Standard coupled mode theory predicts the following. For photonic array of n identical waveguides, each waveguide supports G1 individual guided modes. There will be G1 photonic bands and n array modes in each band. For example, photonic array of 20 identical waveguides supporting each 3 guided modes, 1, 2, 3. There will be 3 photonic bands and 20 array modes in each band. For superlattice containing n identical supercells, in each supercells there are G supercell guided modes of individual waveguides. There will be G supercell photonic bands and n array modes in each band. For example, superlattice of 17 supercells. In each supercell there are 1, 2, 3, 4 guided modes of individual waveguides. There will be 4 photonic bands and 17 array modes in each band. Analytical expressions for the set of envelopes U0. A. Lattice or array of identical waveguides. Set of n approximate envelopes for n array modes of each of the G1 bands can be constructed on the basis of n harmonic functions psi-q, where psi-q as a function of x equals to aq as a function of x times sinus pi q x over n lambda, where lambda is a period of the array and q runs from 1 to n. AQ is 1 for all the q numbers except n, and equals to sinus pi qx over n lambda for q equals to n. The set of u0, which is of the main interest here, can be received from the set of psi q functions by the endpoint discretization of the set of psi q at the geometric centers of the size, namely at the positions x equals to half lambda, 3 half lambda, and so on until n minus half lambda. Analytical expressions for the set of envelopes U0 in the case of superlattice or periodic sequence of different waveguides. Set of n approximate envelopes for n array modes of each of the G supercell bands can be constructed on the basis of n harmonic functions psi q, which have a form psi q as a function of x equals to aq as a function of x times sinus pi q x over n lambda supercell. This is a period of the superlattice or a supercell length, and q runs as before from 1 to n. The amplitudes aq, all amplitudes equal to 1 except the last one, which equals to pi qx over n lambda supercell. Again, the set of the interest u0 can be received from the set of those functions by the endpoint discretization of the set psi q x at the geometric centers of the supercells, namely at the positions half lambda supercell, 3 half lambda supercell, and so on until n minus half lambda supercell. Analytical expressions for the set of propagation constants sigma. There is so-called extended coupled mode theory, extension of a standard coupled mode to the case of infinite photonic lattices and superlattices. It is actually a combination of coupled mode formalism and plane wave expansion. Extended coupled mode implies periodic boundary conditions and assumes in advance that the envelopes of the array modes U0 are plane waves. In the computations, extended coupled mode only accounts for coupling between the waveguides in a single unit positioned at the center of an infinite array with their neighbor waveguides located both inside in case of the superlattice and outside the central unit cell. It does not account for coupling between all waveguides in the array, as it is in the standard coupled mode theory. For this reason, the approach is very fast. The computations require a few seconds to tens of seconds on a standard PC machine. As an input parameter, extended coupled mode requires dominant spatial frequencies kx of the plane waves u0 or wave vectors kx from the first Brillouin zone of the corresponding one-dimensional photonic lattice or superlattice. This allows accurate analytical evaluation of propagation constants sigma and automatically photonic band structure sigma uh, as a function of kx. Nevertheless, this approach does not allow accurate evaluation of envelopes U0 and therefore total model fields E of a finite array. We will use extended coupled mode theory for analytical expressions for the set of propagation constants sigma. Solution of extended coupled mode theory eigenequation for infinite one-dimensional arrays n times for n different incoming parameters kxq, which is equal to pi q over n lambda for lattices, or pi q over n lambda supercell for superlattices. Q, as before, runs from 1 to n, yields a full set of propagation constants sigma. This is the eigenequation. M double underlined as a function of kxq times u0 double underlined equals to sigma times u0 double underlined. M double underlined is extended coupled mode matrix for infinite arrays accounting for periodic boundary conditions. Sigma is an eigenvalue of this matrix. It is propagation constant of an array mode with dominant spatial frequency kxq, and u0 double underlined is a part of envelope function of an array mode of infinite one-dimensional array. It is irrelevant for us. We refer our audience to the references 1 and 2 for the detailed description of the extended coupled mode formalism. You can imagine the main idea of the analytical approximation as the following flowchart. After computation of a set of n guided modes of an auxiliary envelope waveguide and n different dominant spatial frequencies kx, we can input those guided modes and spatial frequencies into the black box number 1, discretize n guided modes of the auxiliary waveguide at the centers of the unit cells, and thus receive a full set of envelopes of array modes U0. Same data we can input into the black box number 2 and use the kx numbers as the incoming parameters for the extended coupled mode theory for infinite arrays. From here we can get a full set of propagation constants of array modes sigma. Array modes ET as a function of x can be reconstructed with the modes expansion conjecture. Photonic band structure sigma versus kx is received automatically with this approach using extended coupled mode theory for infinite arrays. Note that since there are two independent methods for computation of u0 and sigma, computation error in the calculation of u0 does not affect the computation error in the calculation of sigma. The advantages of the approach. First, the approach is very fast. Computation of optical characteristics, namely array modes and photonic band structure, of large one-dimensional photonic crystals, including a large number of coupled elements, lasers or waveguides, become available on the time scale of a few seconds to tens of seconds on a standard PC machine. The computation time is virtually independent on the number of elements in the array. Second, the approach is very accurate. Third, for the first time, analytical prediction of model fields and their associated propagation constants in one-dimensional photonic lattices and superlattices become available. The benchmark. As a benchmark, we used Helmholtz equation. The second derivative of the transverse component of the array mode ET with respect to x plus k0 square n square times ET equals to sigma square ET, where sigma is a propagation constant of the array mode. Nx is the whole photonic array refraction index distribution along the x direction at the position z equals to 0. It is known in advance. K0 equals to 2 pi over lambda 0, wave number of the injected light, known in advance. Lambda 0 is the injected wavelength, clearly known in advance. We are to find ET, transverse component of the array mode electric field at z equals to 0, and sigma, propagation constant of the array mode. The equation was solved in finite differences. Results and discussion. As the first example of application of our analytical approximation, let me show you array of 20 identical single-mode waveguides. N-core for each of the waveguides is 1.51, N-clad is 1.5, unit cell width lambda is 4.5 micrometers, waveguide core width 3.8 micrometers, injected wavelength lambda 0 is 1.55 micrometers. At the subplot A, here, you see the first array mode of the photonic crystal, black curve, coupled mode theory, gray curve, numerical solution of Helmholtz equation. At the subplot B, here, you see the first guided mode of the envelope planar waveguide, gray curve, function psi1, black circles, function psi1 discretized at the 20 points, namely at the centers of the photonic crystal sites. At the subplot C, you see envelope of the first array mode as computed with the exact CMT approach, gray circles, and with the analytical approximation, black daggers. Here you see propagation constants of the photonic crystal under consideration as computed with coupled mode theory, gray circles, and with the analytical approximation, black wildcards. As you see, there is a very good agreement between the two methods. As the second example, let me show you photonic superlattice of 17 identical supercells. Each supercell contains 3 waveguides. Here you see the parameters of the waveguides. They are of parabolic core shape. Each supercell contains, as I told, 3 waveguides and supports for 4 individual guided modes. Single site width lambda is 5 micrometers, supercell width is clearly 15 micrometers. Here you see the first array mode of the first photonic band, black curve, Helmholtz equation, gray curve, standard coupled mode theory. At this subplot, you see the envelope of the first array mode of the first band, black daggers, analytical approximation, gray circles, standard coupled mode theory approach. Here you see propagation constants of the photonic superlattice under consideration. Gray circles, exact coupled mode theory formalism, black wildcards, analytical approximation. As you see, there is a good agreement between the methods. Computation time. In our computations, we use a standard PC machine with Intel Core i7 CPU, 8 GB RAM, and Windows 7 operation system. The machine time required for the calculation of propagation constants, sigma, and model fields, A, of the array modes with the analytical approximation was about 5 seconds for the lattice and 15 seconds for the superlattice. Same calculations with the standard CMT required 10 seconds for the lattice and 30 seconds for the superlattice. Solution of Helmholtz equation in finite differences required about 10 minutes for the lattice and about 30 minutes for the superlattice. Conclusions. First, for the first time, analytical expressions for photonic array modes, model fields, and propagation constants in one-dimensional photonic crystals, namely photonic lattices and superlattices, become available. Second, the analytical approximation allows very fast, a few seconds to a few tens of seconds, and accurate computation of array modes in one-dimensional photonic devices containing a large number of coupled elements, waveguides, lasers. The computation time is virtually independent on the number of elements in the array and almost does not increase with increasing the latter. Third, the analytical approximation allows deeper insight on the influence of different parameters of a photonic devices, such as core-clad contrast and geometry of a solitary waveguide, on the array modes and photonic band structure. Here you see the references related to the research. Here you see the references of our other related research: analytical approximation for two-dimensional photonic lattices and superlattices. Thank you for your attention.